Hello, this is a quick video. I need to talk about some concepts on stability for both continuous system and digital system or discrete time systems. Okay, when we after we make the modeling for the dynamic system, for example for the continuous system, we model the system by different differential equations. Okay, and we model the system in a discrete time system. We model it in difference equation. After that, we go for the Laplace transform on continuous system and end up with some transfer function in the S-plane. Okay, and the Z transform after we go for difference equations and taking a Z transform, and we end up with a transfer function in Z plane. Okay, an example for that, you can see these two models here. For example, we have some form of continuous system in S-plane, or Laplace is in S-plane, we will see it, and digital system in Z-plane. Okay, just I need to clarify something here. So the S-plane, how to say the system in the S-plane is stable or not. This plane here, we have a real axis we call sigma, and the imaginary part we call omega or j omega, because it's a complex number. It has a real part and imaginary part, which is omega here. It could be 2 plus 2j, it could be 3 plus 4j, it could be 5 plus 6j. It's complex number. Of course, it's complex number. It will be complex conjugate. Of course, you will find maybe 2 plus or minus 2j. It's appearing in complex conjugate. If it has complex part here, imaginary part here, so it goes. You will find it into roots here. Okay, unless if it is here and the real axis here, so there's no. This will equal to 0. You have only this part, which is sigma. Okay, so if any root lies here in this part, in the left hand side, any root goes here, it's stable. If you have any root come here, the system is unstable. Okay, the same here in the Z plane. Z it's a complex number, like it has real Z and complex and imaginary of Z. Okay, so Z is a complex number. Oh, okay, so and this is a unity circle, the radius is 1, and the radius magnitude is 1, magnitude is 1. It's a unit circle. If the root is inside this unit circle, the system is stable. All stable poles inside the unit circle. If any pole is outside, like this one, this will make the system unstable. So to ensure the system is asymptotically stable or stable, all the roots is inside the unit circle. We call this also as asymptotically stable. If we have any root outside the unit circle, so the system will be unstable. Okay, so just to repeat, here if we have all the roots is in the left hand side, so we call the system is stable. So if this sigma is negative, so we can say the system is stable. And S is the root, all these are roots for the characteristic equation. Okay, or the poles for the transfer function, the roots of the denominator transfer function. The roots of this one. Okay, this denominator for the transfer function. If the roots for this is in the left hand side, because this is a continuous system, because this is a continuous system and this is a discrete system. Okay, so if these roots are inside, then are in the left hand side, this sigma is negative, so the system is stable. And for the Z plane here, if all the poles, all these are inside the unit circle, so if you can say Z will be equal to 0.6, Z will equal to minus 0.8, and Z will equal to minus, because this will equal to 0, and you find all Z. Okay, so Z is 0.6, Z minus 0.8, and Z will be 0.5. So all these poles are inside this unit circle. You'll find that all these are in the real axis. Okay, because it's 0.6. This, for example, 0.6. So it's all this inside this unit circle. Okay, just if you need to see it using MATLAB, here is square plus 5 is plus 6. So you can make just roots, just make coefficient 1 and 5 and 6, 5 and 6. So you got both are negative, so the system is stable indeed. And the same for this one. It's just clear, it's very clear, it's factored and u equal to 0, so all these are less than 1, and so the system is stable for these both systems. Thank you for watching. I hope this video will be helpful for you, and see you next time.